Hello, hello. I hope everybody has a coffee. Please get to sitting, and we'll get into the next. That was a really tasty yogurt. I don't know if you tried it. Yeah, you tried it? Yeah, very tasty indeed. That's true. Okay, so checking in if we're ready or not. Streaming-wise, not yet. Yes, perfect. Thank you. Well, our speaker is already on the podium. I didn't even have to call him. But we're going to be hearing from a good friend, Eylon Yogev, from Bar-Ilan University on STIR, Reed-Solomon proximity testing with fewer queries. All yours.
Thanks, Daniel, for the introduction. Hi, everyone. I'm kind of excited to be here, the DK proof, and present STIR. This is joint work with Alessandro Chiesa, Giacomo Fenzi, and Gal Arnon, who is not here. And okay, so we're going to talk about Reed-Solomon proximity testing. And please feel free to, just barge in and ask questions. Okay. Yeah. Good. So the basic setup, the motivation, are building snargs in the random oracle model. If you heard Ale's talk in the previous session, then he gave a very nice overview of how you build these snargs from a random oracle, given that suddenly, from the sky, you have an IOP. Okay? So it was that, side of the cliff. And so this is going to be our main motivation. And in this talk, we're going to see the other side. Okay, how do I build at least parts of this IOP? So in our setting, we have a prover, we have a verifier. We want a snarg, so we want it to be succinct. The proof should be much more smaller than the witness. We want non-interactive. We want it to be an argument of knowledge, even with a straight line extractor. And both prover and verifier have shared access to this random oracle denoted here by F. In practice, this random oracle is instantiated with some concrete hash function. These hash functions are efficient, they're very fast. Typically, you get kind of a fast scheme from this. And today, these are used to secure a lot of money on blockchains in various companies. Some mentioned here, some of the people are here. So you're kind of familiar with this. Okay. So just one slide about the BCS information. So Alice gave us a nice overview of this. But in general, we have an IOP. So we have a prover and verifier that talk in many rounds. The verifier has Oracle access to the prover messages. And the BCS transformation takes this and, in this magical way, compiles it to a non-interactive snarg, which is very small and very efficient. And the message I want from this slide is that what we want the proof length of this IOP, okay, to be small, and we want a small query complexity. And this is because these two parameters affect the verifier of the compiled snarg. So if we have more queries, then the argument size is going to be bigger. And if the proof length is bigger, then the argument also is going to be bigger. And also the verifier hashes. So the number of hashes that the verifier needs to perform also depends on the query complexity. OK. And the main building block in these IOPs, so I don't have time to describe exactly how you build them, but in various versions of IOPs, kind of really the bottleneck and the main heavy tool there is a Reed-Solomon proximity test, and this is going to be the topic for today. Okay, so what is a Reed-Solomon code? Okay, so it's here denoted RS, okay, Reed-Solomon, with I have a field F. I have an evaluation domain L, and have a degree D. So what is this code? What are the code words in the Reed-Solomon code? I also have these, forgot, yeah. So we're going to take polynomials over this field, okay, of degree at most D, and we're going to encode them by writing the evaluation of this polynomial on L, on my evaluation domain. And the rate of the code is D over the size of L. Okay? So if my evaluation domain is exactly of size D, kind of this is exactly enough information to reconstruct the polynomial. And if my evaluation domain is much bigger, then I have much more information than I need to just reconstruct the polynomial. So I have redundancy. Okay? And this is how the code kicks in. So just for simplicity, you can think of the rate rho to be like 1/4. Okay? This would be like a typical setting. And if this evaluation domain is something called smooth, then we have like fast FFTs, and we can evaluate it quite quickly. Okay. So what we're going to talk about is proximity tests to Reed-Solomon code. So these are IOPPs. These are IOPs of proximity. So the setting is the following. We have a function f in the sky. The verifier has oracle access to this function. Okay, so it can query this function at some point x and get back the output f of x equals y. We, of course, want to maintain a small number of queries. And the prover is trying to convince the verifier that this function is indeed a Reed-Solomon code word. This is indeed an evaluation of some polynomial of degree at most t. Okay? So they're going to talk. The prover is going to send a message. This is going to be IOP. So the prover is going to send some maybe long message. The verifier just has oracle access. In addition to the function, has oracle access to the prover messages. He can send some randomness. They talk for a few rounds. And what are the properties that we want? Okay, so these are properties similar to property testing. We want that if f is indeed a code word, then the verifier is going to accept with probability 1. And if f is very far from the code word, then the verifier is going to reject with high probability. Okay? Any questions at this point? And I can. Okay. Kind of annoying. Okay. And yeah, and our goal is to really minimize the number of queries that f performs, either to the function f or to the oracle queries. Okay? This number of queries is going to directly translate to the size of our snark and to the complexity of the verifier. Okay. So I'll start just by showing our main result. We give a new IOP of proximity for Reed-Solomon codes. We call it stir. Okay, we're going to see why the name. The number of rounds that this protocol has is log D, so logarithmic many rounds. The proof length is O of L, so kind of linear in the object that I'm testing. Okay, so there's no like a big blow up there. And the query complexity of this protocol is this crazy formula that I written here, which is roughly lambda, which is like the security parameter, it's like 128, okay, times log of this expression, log D over minus log square root rho, okay? And this is the number of queries you get without any conjecture. This is like provable security. Here I'm assuming that, the distance is this, the distance that happens in practice, which is, 1 minus square root rho. This is like the bounds that we can get to. Okay. For a quick comparison with phi is kind of the, today, very popular IOPP for Reed-Solomon, okay, used in many systems. So the query complexity, okay, written in this terminology for phi would be lambda times, okay, do I have a pointer here? Yeah. Lambda times this expression, and if you can compare the two, you see that the difference is this log that we have. Okay? So we have much fewer queries. Okay, yeah. Yeah, so D is like the degree of the function you want to test. which is kind of the size of the computation that you're proving, okay? We're going to see examples now, but D is like 2 to the 20, 2 to the 25, stuff like that. Okay, so we have this theoretical result, but what about practicality? Like what constants are hidden in this O? So I'm going to compare this so we have a practical implementation. We implemented this in Rust, okay, using the ArcWorks framework. For our benchmark, we use a 192-bit field, 256 hash. I want to kind of emphasize, when I'm showing this comparison, we did a very, as optimized as possible we could do for steer and for fry, okay? So we took all the optimizations that we know and can be shown for fry, and only then kind of try to compare it to steer. Yeah. And the code is available online. It's kind of nicely written, but again, this is for academia. If you want to really rely some blockchain on it, then maybe you should, go over it once again at least. Okay. So let's do a more deep comparison, okay, with Phi before I dive into more technical details. So this is a drop-in replacement for Phi. So any system that uses Phi can, if it wants, replace and use steer. We have fewer queries, and again, this is the comparison of the number of queries, and this leads to fewer authentication paths, okay, in the BCS compilation, which means a smaller argument size, and also a smaller query complexity. So the verifier needs to verify all the authentication paths of the Merkle tree, and since you have less of them, you have much less hashes, okay? And once you have a less hash complexity, it means that the verifier is faster and also more recursive friendly. So if you use the verifier in a recursive system to prove something about it, then it's much easier. Let's see some examples, some numerical examples. So yeah, say the degree is 2 to the 20 and the rate is like 1/4, and we're targeting, let's say, 100 bits of security. You can always kind of get more security with a proof of work, but just put in some simple numbers here. Then Phi would have roughly 400 queries, where steer would have roughly 200 queries. And the prover in both cases would have a very similar runtime. So we're going to see the runtimes. Steer is ever so gently slower than Phi, but really the main bottleneck in these systems is from the initial evaluation of the function that we want to test. Okay, this is kind of the bottleneck, and this is not changed between steer and Phi. Okay, so this is the same for both. Yeah, so we get better argument size and verifier hash complexity across almost all parameter regimes. Okay, this is not like I didn't cherry pick some specific numbers. And we get larger and larger improvement as the degree becomes larger. So for example, here I took the degree to be 2 to the 24 and rate 1/4. Okay, the size of Phi would be 177 kilobytes, and the size of steer would be 107 kilobytes. Okay, that's quite a big improvement. The number of hashes that the verifier performs, okay, 3.5K for Phi and 1.8K for steer. Another example where the degree is higher, yeah, 2 to the 30, I can't see well. So this is like a computation of size 2 to the 30. This is quite a big computation. So here Phi would be almost like half a mega, okay, 500 kilobytes, and steer would only be 200 kilobytes. Okay, and you can see almost a difference of 3 in the number of hashes. Okay. Here are, I heard you guys like graphs, so here are some graphs. So you can see it's hard to point, yeah. So this is the red would be Phi, the blue is a steer, okay? So you can see here the difference, and the x-axis is the degree. You could see the difference in the argument size, in the verifier hash complexity. You could see the difference in the prover time, okay? So they're quite similar. And this is actually the verifier running time. So for the most of the like higher and important degrees, then the verifier is actually much faster. Okay, any questions about the comparison? Yeah.
So this comparison refers to the standalone setting, no? So have you tried some recursive? So what happens if you try to do recursion of this?
That's an excellent question, yeah. So yeah, this is a comparison for a standard setting, just running the two protocols on some function f. We didn't test with recursion. That really depends on how you implement and do this recursion. And so I don't have parameters for that. I can just imagine because of the faster and lower complexity verifier, you get like significant results there. Okay, excellent. Yeah.
Just on a similar question, do you have any idea what the recursion threshold would be?
What do you mean recursion?
The recursion threshold is the sort of the minimum size of a circuit that could verify itself.
Yeah, I don't know how to. Yeah, good question. Okay, let's see how I'm doing time. Okay. What about conjectures? So if you're familiar that phi has like two versions, one is provable and one is conjectured, then kind of steer borrows the same effect. So either you have the provable version or you can assume a conjecture. And the difference in the number of queries, if you notice, it's instead of the square root row, you just have a row. Okay? And this kind of improves by a factor of 2 the number of queries. Okay? So this is like orthogonal. This is both hold for phi and steer. Okay. So let's see a quick overview of the techniques. I don't think we'll have time to see everything. So I want to give like a very short, rough overview of what happens in phi, and then we can see how steer like does things differently. So there is this folding operation, which folding is kind of a very overloaded term. So forget about what you think folding is, okay? I'm like kind of redefining it here. But it's a natural recursive step that if I want to test a Reed-Solomon with an evaluation domain L and degree D, okay, I want to recurse and reduce it to some other problem, which is still Reed-Solomon, but with degree D over K, and which are evaluation domain L to the K. Okay, good. Well, L to the K is some subset of L of size L over K. So K is some constant, think of 8, okay? Say K is of constant 8. So I managed to, with this folding operation, I can reduce the problem of testing Reed-Solomon of degree D to degree D over 8. And the domain also shrinks by the same factor 8. And, okay, and this is the folding parameter. This is a randomized process. The verifier needs to sample some randomness alpha, send it to the prover, and then I have this folded function, which we denote by the fold of f with parameter k and alpha. And this folding is local. This is very important. So the folded function, how does it compare to f? You kind of, if you want to query the folded function, there is a local mapping that you can query like k places in f, and from them you can compute the folding. Okay, so we have like local access to this folding function, and it preserves distance. So if f was delta far, then except with some small probability over alpha, and this error is kind of, if you're familiar with the proximity gaps, comes from there, then this folding is going to maintain the same distance. Okay, so this is a basic folding operation. I'm not going to dive into how this folding works. But with this folding, and again, this is not exactly the phi protocol, but like a very rough overview. What phi does is says, OK, let's start with some function. I have my function in the sky. I'm now going to denote it f0. And the verifier is going to send randomness alpha 1. And this is going to define the folding, okay, of f0, which we call here f1. f1 is just the folding of f0 with the randomness. And then we do this again. We send new randomness, and we get another folding of f1. This is f2, and so on. Okay, so Fi is going to be the fold of Fi minus 1. And this is, the protocol continues until the degree becomes, some constant, 2. And when the, degree is small enough, the prover just sends the, the polynomial as a polynomial. Okay, just sends the coefficients. And this is like a high-level overview of what happens. And then in Phi, like, what do I need to do? I need to test that the prover actually sent me the folding of F0. Like, I need to test that F1 is actually the folding of F0. Okay, and then F2 is actually the folding of F1, and so on. So we're going to do these consistency checks. And I just want to emphasize that if you invest T queries to do this consistency check, then the soundness error that you get is rho to the T over 2. Okay? This over 2 comes because it's actually square root rho. Okay? And rho is like your rate. So if the rate was 1 over 4, then you get this soundness. And if you choose rate 1 over 16, like, then you can perform less queries. Okay? So the rate gives you like a trade-off between the number of queries and the running time of the prover, okay? Because if you have like rate 1 over 16, the prover needs to send a much bigger evaluation domain. So this is roughly what happens in Phi. Good. Now I want to move to talk about steer. So steer stands for shift to improve rate. And we're going to see what this means. And the main idea of steer is the following. What we're going to do a small recursive step, just like Phi. But we're going to reduce the Reed-Solomon with elevation domain L and degree D to a Reed-Solomon where the degree is D over K, but the evaluation domain is just L squared. So the size of L squared is just L over 2. Okay? So we kind of decoupled this 2 with this K. Okay? Why is this helpful? Okay? This means that for the new code, we have a new rate because we didn't maintain the ratio between how much we decrease the degree and how much we decrease the evaluation domain. So the new rate, rho prime of this new code, is going to be 2 rho over K. So if K equals 2, then they just cancel out and we have the same rate. But if K is like 4 or 8, which is kind of the setting used in practice, then we get something that I call the improved rate. Okay? It's improved only in the sense that we need now less queries for this rate. Okay? And still notice that the evaluation domains kind of still go down by half, and in the next round they're going to go down by half. So overall, the entire sum of size of elevation domains is going to be linear. This is like a geometric sum is going to be linear. Okay. Good. So what does this mean? Okay. Then, we also preserve the distance. Fine. So I just get to what I mean. I mean that the round-by-round soundness, okay, of the steer protocol is going to be as following. So the soundness for every round I, 5 minutes, great, okay, is going to be rho I to the power of Ti over 2. So we don't have one rate. We have rho 0, which is the initial rate of the function. And then every round, we kind of have a different rate rho I. And so the number of repetitions we need also changes. So these are the rows. And then this means that if you solve this, okay, in all rounds, we want security 2 to the minus lambda. So it means that Ti, the number of queries we perform in round I, is going to be this lambda over, log 1 over square root rho I. And let's see just an example, okay? So take K to be 16, okay? Which is kind of what we have in our implementation. And say that the initial rho, okay, the initial distance is, the initial rate is half, okay? And I want 100 bits of security. This means that the rate of the next code is going to be 1 over 16. And the rate of the code after that is going to be 1 over 128, and so on and so on. Okay? So these are like the rates of the codes that we get between rounds. And this means that T0, this is the number of queries you need to perform in the first round, is going to be 200. And in Phi, this 200 just remains for all the log D rounds. Okay? Here we have this 200 only in the first round. In the next round, we're going to have T1, which is only 50. okay, because the rate is 1/16. And in the next round, we're going to have only 29 queries and so on and so on. Okay, and kind of converges to some number there. And again, we have these amazing rates without making the prover run in more time. Okay, still the evaluation domains decreases in every round. Okay, they just don't decrease by the same rate that the rate decreases. Okay. How much time do I have? 4 minutes. Okay, so I have got like 4 minutes to give you a sense of how we do this. And we also already saw folding, okay? So we know that we can kind of shrink the evaluation domain and make the degree go from D to D over K. What we want to do is kind of take this and shift the problem to a larger evaluation domain that has size L/2, not L/K. And this, we call this domain shift. Okay. So we have, so you can capture this problem as following. You have a proximity test for some domain L star, okay, which is bigger than L. And I want to do a proximity test for F over L. How can I move my problem from L, okay, which is very small, to this L star, which is much bigger? So this is kind of the main technique that we do, we call a domain shift. So we're kind of going to shift the problem to a bigger domain. You know, the challenge, of course, we can ask the prover, you know what, prover, just, it is supposed to be a polynomial, just evaluate this polynomial over this L star and give me, okay, give me the evaluation. And this is fine for the honest prover, but we kind of want to in the function we have on L and the function we have on L star. And the question is how to enforce consistency. And what we're going to do, we're going to use this technique called the quotient. And so just how much time do I have? Like 1 minute. OK. So yeah, we're going to skip quotient. OK, I have 1 minute. OK. So I'm going to skip quotient, but I'm just going to say that the main idea of the domain shift is going to tell the prover, oh, please give us a function, now I call it G, okay, on L star. G is supposed to be the same polynomial that represents F, okay, but I don't know, it's a malicious prover might send like a completely different function. And then we're going to perform T queries, not T, Ti, okay, so we're in round I, we have rate I, we're going to perform Ti queries. And we're going to quotient G and all these points that, that we queried. So the verifier is going to query the function f, and all these points xi is going to get yi. And then we're going to define a new function g star, which is g quotiented on all these points that we have. Okay? And g star is going to be the function that we send to the recursion, that we're going to send to the next iteration of the protocol. And yeah, I'm going to skip this. OK, so just the final protocol, how does it look like? We have a function f, okay, that we want to test. What we're going to do in one step, we're going to fold and shift the function. So instead of just folding and folding and folding and checking consistency, we're going to, in one step, fold and shift it to a larger domain. So this would be one step of an iteration of stir. And so we have this function g star, and then we're going to recurse on g star and do this again and again. Yeah. OK. So just to conclude, we had a short time to talk about domain shift and quotient, and I didn't have time to talk about out-of-domain sampling and all these other and the properties of folding. We saw the performance of stir as a replacement to fry with fewer queries and better hash complexity. There's much more that we didn't talk about, like degree correction. How do you make sure that all the degrees are correct? We also have a high soundness compiler. So if you give me like a protocol in the poly-IOP model, I can use this to very efficiently and maintain high soundness and compile it to a protocol in the standard IOP model. And okay, just lastly, I'll end up with some future questions. What can we say about small fields? Okay, can we have a version of STIR maybe similar to this Circle-Stark protocol? Can we have a kind of equivalent of a base-volt version of STIR? Maybe a STIR over binary fields? And lastly, I want to talk about this log-D barrier. So Fry and STIR both have still log-D rounds. And actually, in a previous work, we showed a different protocol that achieves log-D round complexity. However, this work was kind of more theoretical and less efficient, and kind of getting a very practical scheme that has log-D queries is kind of, I think, an interesting open problem. Okay, so I'll just conclude that there's a lot of exciting things coming up, and use STIR. Thanks.
Any questions?
Yeah. Here.
Why is it efficient to do one domain shift and one fold? Why not more domain shifts? Why not fewer?
Why not more?
Yeah, why not more or fewer? Why is the number of domain shifts the same as the number of folds?
The number of, I can't hear you.
Why is the number of domain shifts the same as the number of folds? So why are you doing those two steps always together?
Okay, good. So, I have no reason, if I have a function, I have like no reason to shift it. Okay, I want to first decrease the degree. Okay, I only know how to decrease the degree while decreasing the evaluation domain. I do not have like a direct folding operation that decreases the degree, but maintains the same evaluation domain. Okay, with local access. And so kind of what we do, it really is one operation. So it never sends the folding. Okay, this is like a virtual function that's going to be defined, but not physically sent. So it kind of decrease and then extend.
Thank you.
So they come together.
Okay, let's thank the speaker one more time. So just a quick reminder. I know that there was a question here on the time left. There's like 25 minutes of